This presentation introduces Splannequin, a novel method for freezing monocular mannequin-challenge footage using dual detection splatting. The Mannequin-Challenge became a viral internet phenomenon where participants freeze in place while a camera moves freely. The goal is to create a perfect freeze time effect, similar to the bullet time sequences seen in films like The Matrix. However, there's a fundamental problem. Real-world recordings inevitably contain slight human motions. People cannot hold perfectly still, and these micromotions create significant artifacts during 4D reconstruction. So why does solving this problem matter? High-quality frozen scenes can serve as cleaner data for dynamic scene models. The visual effects industry needs affordable solutions for creating freeze-time footage. Media production and virtual reality tours would benefit from accessible freeze-time technology. These are the motivations driving our work. These visual artifacts come from a core issue: sparse temporal supervision. Static methods are not designed to handle micromotions. In monocular sequences, Gaussian primitives only get training signals when they actually contribute to the rendered image. When a Gaussian is occluded or moves outside the camera's view, it gets no supervision at the timestamp. The spacetime diagram on the right illustrates this. The diagonal dashed line shows standard dynamic rendering, where the camera trajectory naturally provides supervision over time. But freeze-time rendering follows a horizontal line at a fixed timestamp, t star. Along this line, many Gaussians fall into poorly supervised region. The red area marks where the camera has already passed. Those are hidden Gaussians. The blue area marks where the camera hasn't yet given clear views. Those are defective Gaussians. Rendering at these unobserved timestamps leads directly to the ghosting and blur we see in current methods. We identify and correct two distinct types of ill-supervised Gaussian primitives. The first kind is hidden Gaussians. They sit outside the camera's view because the camera has moved past them. Since they are no longer visible, they don't get proper supervision. To fix this, we anchor each hidden Gaussian to its earlier well-observed state using L2 and L1 marks. The second kind is defective Gaussians. They stay inside the camera's view but barely affect the render image. These also don't have good supervision. For them, we anchor each one to its better observed future state. Our pipeline has three main stages. First, we initialize point clouds from the input monocular video. Second, we feed these point clouds and timestamps into a dynamic Gaussian splatting model. This is where the dual detection losses work. For hidden Gaussians at time t, we anchor the parameters theta to an earlier reference time t prime, where t prime is less than t. For defective Gaussians, we do the opposite. We anchor them to a future reference time where t is less than t prime. Both use confidence weighting based on temporal distance. Third, once training finishes, we render the freeze time video by locking all Gaussians to a single user-selected timestamp t star. The camera moves along its original path, but the scene stays perfectly frozen at that moment. Visual comparisons demonstrate the effectiveness of our approach across three state-of-the-art baselines. In each case, the baselines produce noticeable ghosting and blur around moving subjects. Our method removes these artifacts and shows crisp, temporally consistent results with fine details preserved. Splannequin solves a challenge that's never been addressed before: creating high-fidelity freeze-time reconstructions from casual monocular videos. What used to require $750,000 camera rigs now works with a single camera. We introduced three contributions. First, a framework built specifically for freeze-time synthesis, not motion preservation. Second, dual detection regularization that finds and stabilizes ill-supervised Gaussian primitives. Third, real-time rendering. The method has several practical advantages. It's architecture agnostic, so it integrates with existing dynamic Gaussian splatting methods. It runs in real time at over 280 frames per second on an RTX 4090 GPU. Users keep full control over which timestamp to freeze, and there is no inference overhead since deformation runs only once for the chosen timestamp. For more details, please visit our project page.